Hello again, this is Professor Roman. Let's continue the lecture series, Transition to Advanced Mathematics. It's time now that we talked about a branch of mathematics known as combinatorics. Sometimes it's referred to informally as the art of counting. As it happens, there are many simple-sounding counting problems that as yet have no solution. Let me give you an example. Suppose we want to count the maximum number, which I'll denote by k of n, of non-overlapping triangles that can be formed in the plane using n straight lines. This problem is known as the Cobon triangle problem because it was first stated by Cobon Fujimura. I don't know, frankly, when. His dates are 1903 to 1983, so obviously sometime in that period. Here are three examples. If we have available one line, we can't make any triangles. Two lines can't make any triangles. Three lines, the most number of triangles you can get out of three lines is one triangle. You won't get any if the three lines are go through the same point. Then you get no triangles. But if you spread them out a bit, you can get one triangle. If you have four lines, then this arrangement of the four lines will produce two triangles. And there's no other arrangement of the four lines that would produce more. So two triangles is the most you're going to get. I haven't proved this, but it's nonetheless true. If you have five lines, and you arrange them in this pattern, you can get five triangles. So hopefully that gives you the idea of the problem. If you have n lines, what is the most number of triangles you can get by careful placement of those lines in the plane? The only known values for the Cobon triangle problem are for n equals 3, 4, 5, 6, 7, 8, 9, 13, 15, and 17. If we have any number of lines equal to one of these, we know how many triangles are possible, the maximum number. So we know k of n for these values of n. That's all we know. So clearly we are a long way from a complete solution to Cobon's triangle problem. Evidently the right ideas, the key ideas, have not occurred to anyone as to how to solve this problem. We do have some upper bounds that are known for these Cobon numbers, let's call them k of n. A gentleman named Saburo Tamura has shown that k of n is less than or equal to, I'll explain these brackets in a second, but there it's read the greatest integer in n times n minus 2 over 3. So this sort of partial square bracket, there's a little hook at the bottom but nothing at the top. This is called the greatest integer function. So the greatest integer in x is just like it sounds. It's the largest integer less than or equal to x. So for example, the greatest integer in 1/2 is 0. The greatest integer in 5/2 would be 2, and so on. Sometimes this is called the floor of x as well. we're going to encounter this again. Actually, we did encounter it, didn't we, when we talked about binomial coefficients. So we've seen this before. Subsequent to Tamura's contribution of this upper bound, the upper bound was improved slightly by two mathematicians who showed that Tamura's upper bound can be lowered by 1 when n has this form. So the remainder upon dividing n by 6 is either 0 or 2. The reason I mention this, it's not something I expect you to remember. I doubt very much that any other professor includes this in their class on transition. So you don't need to worry about this. You don't need to worry about the Cobon numbers at all, because we're not going to discuss them further. In particular, you don't need to worry about these upper bounds. But what I wanted to point out to you is that difficult mathematics problems are not just one day solved. It doesn't usually work like that. Nobody gets complete and total insight that easily, that quickly. What happens with complicated math problems, like the Cobon triangle problem, like some of the other problems we discussed, the twin prime problem, the Goldbach conjecture, is that mathematicians make slow progress towards a solution. So progress towards finding the exact values of the Cobon numbers is finding an upper bound or a lower bound for them. So what will typically happen, just to make up some numbers here, is you have a counting problem that's very hard, and you might discover that the number you're looking for, somebody might discover the number you're looking for lies between 50 and 100. And then another mathematician will come along and say, well, I can actually close those bounds and prove that the number we're looking for is between 50 and 90. And someone else will come along and squeeze those together. It'll be between 55 and 85. And there's a slow progression of better and better results that hopefully someday leads to a complete solution. So we have many problems, not just counting problems, but problems throughout mathematics, where we don't have complete solutions, but we have, I guess you could call them partial solutions, or at least, better to say, significant progress towards a complete solution. I'll discuss with you another unsolved counting problem in much more detail so you can see the kinds of things that are going on at that level. It's not something you need to know for this course, but it's an interesting digression. I think you might find it interesting. So let's settle down, however, and look at the basic techniques for solving counting problems. Throughout this chapter, in fact the rest of the book, I'll denote the size of a finite set S by putting vertical bars around it. So if S has n elements, then the size of S is equal to n. Another term for size is cardinality, a term we'll get quite familiar with later on in the course. The simplest rule for counting is called the sum rule. And it's a rather obvious rule, so it's important but not very difficult to understand. It simply says that if A and B are disjoint sets, finite sets, then the size of the union is the sum of the sizes. I should add finite here. Okay? This is a disjoint union. Then, if you remember, I discussed that with square. So I could have written it this way. Perhaps I should have, but it doesn't matter. It's correct either way. The general rule is if you have n sets and if they are pairwise disjoint. Disjointness is not strong enough. It must be pairwise disjointness. And we take their union. Again, this is a pairwise disjoint union. Then the size of the union is the sum of the sizes. This is, as I said, pretty obvious, pretty straightforward. However, at this time, we cannot give a formal proof because that would require that we formally define the size or cardinality of a set, along with what it means for two sets to have the same size. We also haven't formally defined the notion of finiteness, a finite set. So all that has to be done before we can do a formal proof of the sum rule. So I can't give you that now, but I have to believe this rule is so obvious that you shouldn't have any real trouble with it. If you have two sets that have no elements in common, one has 4 elements, the other has 5 elements, then their union has 9 elements. The sum rule then tells us that a disjoint union, I'm going to change these to symbols to disjoint symbol. Disjoint union is the sum of the sizes. If the sets are not disjoint, we can still get a formula for the size of the union. It is the sum of the sizes, but that has created an overcount because every element that lies in both sets has been counted twice. To fix that, we just subtract the size of the intersection. And I drew a picture here to help you with that. The size of the union here would be the sum of the two sizes of A and B, but the elements in region 2 here are counted twice, so we have to subtract. This formula is called the principle of inclusion-exclusion for two sets. It'll become a little more meaningful, this term, when we look at 3 sets. What is the size of the union of 3 sets? Well, if we add the sizes of the 3 sets, again we have overcounted. Unless they're pairwise disjoint. But assuming that we don't know, this is a possible overcount. Elements that are in A and B are counted twice. Elements that are A and B are counted twice, so I can correct that count by subtracting the intersection. Elements in A and C are overcounted, so I can subtract this intersection. Elements in B and C are overcounted, I can subtract this. The problem is I may now have actually undercounted because the elements that are in all 3 here were counted 3 times by this sum, but then subtracted 3 times. So they're at 0. So I have to add back the size of the intersection. And again, here's a picture. size of A plus size of B plus size of C counts the elements in regions 1, 2, and 3perfectly. But an element in 4 is counted twice, so I have to take that back by subtracting the intersection, the size of the intersection of A and B. Same for region 5, counted twice in B plus, the size of B plus size of C, so I subtract the size of the intersection. These are counted correctly, same thing for 6. But in the process of doing that, the elements in region 7 here are not counted at all, because they were counted once for A, once for B, once for C. Subtract once for A intersect B, once for A intersect C, once for B intersect C, so the net result is 0. So the elements in region 7 have to be added back. So what's going on here, you see, in this formula is that you include the sizes of the individual sets, you exclude the sizes of the intersection of pairs of sets, and you include the intersection of all three. So that's where the term principle of inclusion-exclusion comes from. Incidentally, looking at the Venn diagrams and the discussion I just gave you is not a formal proof, and I'm going to leave that for you. You want to prove those equalities are valid, you'll have to come up with something more formal than just look at the Venn diagram. Okay. Frankly, what it's going to amount to is a formally written description of pretty much what I said. Okay. Here are some examples of the use of the principle of inclusion, exclusion, and counting. It's a very useful formula. There are whole chapters in books on combinatorics devoted to this principle. It's also very useful in probability theory. So it is quite an important formula. And it applies not just to 2 sets and 3 sets, but to any number of sets. If you had 25 sets and you wanted to know the size of their union, you would add up the sizes of the individual sets, subtract the sizes of all the pairs of sets, and there are 25, choose 2. The binomial coefficient 25, choose 2 pairs, you have to subtract their sizes, the intersections. Then you have to add back the sizes of the intersections of 3 at a time, subtract the sizes of the intersection of 4 at a time, add and subtract, go back and forth until you until you're either adding or subtracting the intersection of all 25. The sizes of the intersection of all 25 sets. So the pattern is exactly the same. So let's count the number of integers between 1 and 6,000 that are divisible by either 3 or 5. Okay. Number of integers between 1 and 6,000 that are divisible by either 3 or 5. So to do this, we start with the universe, and that's the set of integers between 1 and 6,000. Let d sub 3 be the integers in this universe that are divisible by 3, and d sub 5 to be the integers in U that are divisible by 5. What we're looking for, what the question asks us to find, is the size of the union, because the union is the set of all integers between 1 and 6,000 that are divisible by either 3 or 5. And this is the formula. So we need to compute these 3 sizes. Well, the intersection is the set of integers in U that are divisible by both 3 and 5. And since 3 and 5 are relatively prime, this is the set of integers that are divisible by 15. So I'll call that d sub 15. Well, one way to determine the size of these sets, for example, D3, it might be a little tricky at first, but the key here is to write the sets down in a more transparent form that will show you the size. For example, D3, that's the set of all integers that are divisible by 3, or in other words, the set of all multiples of 3 that lie between 1 and 6,000. So it's 3 times 1, 3 times 2, 3 times 3, all the way up to 3 times 2,000. When you write the set this way, it becomes evident. There are 2,000 of these. Similarly, D5 is the set consisting of 5 times 1, 5 times 2, 5 times 3, up to 5 times 1,200. So there are 1,200 of those, and D15 has only 400 elements. So we can now plug into the formula and get 2,800. So there are 2,800 integers between 1 and 6,000 that are divisible by either 3 or 5. Now I can hear some of you saying or thinking, who cares? Well, that's not an unreasonable thing to say. There are two types of people who care, I guess you might say. There are mathematicians and other people who study numbers and need to know things like this for reasons that vary. But it's possible. Somebody who, even someone who is a finance person might want to know. These are dollar amounts for some reason. And then there are the mathematicians and others who just think that it's amazing that we have enough knowledge to be able to compute something like this without sitting down and looking at each of the 6,000 numbers and trying to divide them by 3 and 5 to figure out which ones are so divisible. So this is the power of mathematics, the power of human thought that enables us to construct arguments like this and discover things in ways that are relatively simple. And it's just, it's something that mathematicians do. Okay. Here's another example. Among 50 patients in a hospital, 25 tested positive for pneumonia, 12 tested positive for bronchitis, 20 tested positive for COVID-19. 8 tested positive for both pneumonia and bronchitis. 6 tested positive for pneumonia and COVID-19. 7 tested positive for bronchitis and COVID-19. 3 tested positive for all 3 diseases. Okay. So we want to find the number of patients who have at least one of these diseases and the number of patients who have none. Okay. So let U denote the set of patients, so that's our universe. Let P denote the set of patients with pneumonia, B is the set of patients with bronchitis, and C is the set of patients with COVID-19. So we know the sizes of these individual sets, and we are given the sizes of these intersections of pairs as well as all 3. So the number of patients with at least one disease is the size of this union, And by the principle of inclusion-exclusion, we have all the numbers given to us. We plug them into the formula. 42 patients have at least one of the diseases, which means 8 patients are disease-free. Okay, let's move on to another counting technique. We have the sum rule, and we have its very important extension, and that is the principle of inclusion-exclusion. That applies to any sets. The sum rule applies only to pairwise disjoint sets. The fundamental counting principle is, well, fundamental to the study of counting, and it is best phrased in terms of performing a sequence of tasks. And we want to know how many ways there are to perform the entire sequence of tasks. Of course, we have to know how many ways there are to perform each task separately. So here's the formal statement. Let T1 through Tn be a sequence of n tasks with the property that for each k between 1 and n, the number d sub k of ways to perform task t sub k does not depend on how the previous tasks in the sequence were performed. This is an independence requirement. You can perform task 1 and task 2 and task 3. When you come to task 4, the number of ways to perform that cannot depend on how the first 3 tasks were performed. It can depend on the number of ways to perform the first 3 tasks, but not on the way that you actually do perform those tasks. This will become more comfortable for you as we do examples. But some form of independence is required here. The conclusion is that the number of ways to perform the entire sequence of tasks is the product, d1 through dn. The fundamental counting principle is also known as the multiplication rule, by analogy with the sum rule, or sometimes even the product rule. Problem with that is if you've taken calculus, then you know there's a product rule in calculus, and so the term product rule can be a bit ambiguous. So I like the fundamental counting principle. I think that's a good name for it. In the past, the state of California issued license plates consisting of 3 digits followed by 3 letters, shown here. And repeated digits and letters are allowed. How many license plates are possible? Well, it's good to try to visualize these problems somehow in your mind. Visualize yourself in prison. And you've been assigned not to the laundry or the kitchen, but to the license plate factory. And you are told, make a license plate. What are you going to do? First, you're going to choose what you want to be the first digit. That's your first task. Excuse me. Then you're going to choose the second digit for the plate, then the third digit, then the first letter, then the second letter, then the third letter. That's how you're going to construct your license plate. You have to perform 6 tasks. Moreover, the number of ways of performing each task doesn't depend on how the previous tasks were performed. Now, by contrast, if the rules were more complicated, say, for example, the rule for making a license plate says if you use a certain digit in one place, the next digit cannot be adjacent. So if you use a 3, you can't use a 2 or a 4 for the next one. Then if you think about the first task can be performed in 10 ways. You can put 0 through 9, okay, assuming 0's okay. But if you choose 0 for the first digit in the plate, you've got 9 other choices for the second, because you can't use a 1. That would be adjacent. But if you chose a 1 for the first position, then for the second position you can't use either a 0 or a 2. You've only got 8 choices. So depending on what you pick for the first digit, that will affect the number of choices you have for the second digit. That would violate the requirements of the fundamental counting principle. We don't have that problem here. There's no strange restrictions on which digits can be used. So you've got 10 choices for the first digit, 10 for the second, 10 for the third. Then you've got 26 choices for the letters in each case. Fundamental counting principle tells us then you multiply these numbers together, 17,576,000 license plates. Let me give you another example where the independence aspect of the fundamental counting principle is critical. Excuse me. Let's suppose you want to buy a personal computer. You've narrowed the choice down to 3 possibilities. After you've made that choice of computer, you then must choose a type of memory that's compatible with the motherboard in the computer. So just as a simple example, let's say computer A can use memory of types A1, A2, A3, or A4. Computer B can use these memory types, B1 through B4. Computer C can use these memory types. So the choice of memory does depend on the choice of computer. First task is choosing the computer, second is choosing the memory. The second task of choosing memory does depend on how you do the first choice, but the number of choices of memory does not depend on how the computer was chosen, on which computer was chosen. So the fundamental counting principle applies. And you can say there are 3 ways to choose the computer, 4 ways to choose the memory, therefore there are 12 choices for both. But this would fail if, for example, computer B was only compatible with 3 different memory types. Now, not only does the choice of memory depend on the choice of computer, but the number of choices for memory depends on the choice of computer. You cannot use the fundamental counting principle. Okay, let's look at another example. To count the number of 3-digit numbers, so hundreds place, tens place, units place, with no repeated digits. Again, use your imagination. Think of actually constructing a 3-digit number. You're going to perform 3 tasks, choosing a digit for each of the positions in the number. One possibility would be to choose the hundredths digit first, then the tens digit, then the ones digit. Okay? There are 9 choices for the hundreds digit. since you can't use 0, you won't get a 3-digit number, you'll get a 2-digit or 1-digit number. So 0 is not available for the hundreds place, or you wouldn't have a legitimate 3-digit number. So you've got 9 choices for the hundredths digit. And it can also help now to imagine making a choice. Say we chose 3. So we start with a 3. How many choices for the tens place? All 10 digits would be available except 3, the digit you put in the hundredths place. So you've got 9 choices for the tens digit. 0 is now a possibility, so there are initially 10 digits, but you can't use the digit you used already, so you got 9 choices. So let's say that's 4. How many choices do you have for the units place? 10 minus 2. You've got all 10 possibilities, but you can't use a 3 or a 4. So you've got 8. So the fundamental counting principle applies. The independence portion is satisfied, so you got 9 times 9 times 8. 648 3-digit numbers with no repeated digits. What if we change the sequence of the tasks? Suppose we first choose the units digit. There are 10 possibilities. Then you come to the tens digit. You have 9 possibilities because you can't reuse the one you chose for the units. So 10 followed by 9. Now we run into a little problem. The number of possibilities for the hundredths digit depends on the particular choices made for the units and tens digit. Specifically, depends on whether or not 0 has been used. If it's been used, you can't use 0 for the hundredths digit. So if it's been used, that really has no effect on the number of choices for the hundredths digit. If it hasn't been used, then you have to reduce the number of choices by 1, because 0 is still available, but you can't use it. Okay? So if we're going to solve this problem using this sequence of tasks, we have to be a little more careful. What we can do is we can partition the set of possible 3-digit numbers with no duplicates into 3 blocks. So or groups if you prefer. Here's the first group. 0 went into the units, therefore obviously the tens digit is a non-zero number. 0 went into the tens digit, so obviously this is a non-zero number, or you didn't use 0 at all. So basically, you used 0 in a different place, or you didn't use 0. Each of these cases now is amenable to the fundamental counting principle. First of all, though, note that these are mutually exclusive. They're pairwise disjoint. There's no 3-digit number that's in common, say, to the first 2, because 0's here, but 0's over here, and so on. Which means the sum rule applies, and so the total number of 3-digit numbers with no repetitions is the sum of the sizes of these 3 sets. So all we need to do is focus on each one of these separately and count. The first case, 0 is chosen for the units digit. There are then 9 choices for the tens digit. So we have, let's say you put a 4 in the tens digit. So far your number looks like this. Okay. How many choices here? 8, because you've used 2 of the 10. And you've used 0, which means you don't have to exclude 0 from the hundredths digit. It's already been taken. So you have 8 more. So you have 8 times 9 times 1, because you've chosen 0. This is given. This was just an example of what, if maybe you chose a 4, maybe you chose a 6, whatever, but you've chosen something here. So you've got 9 choices for this one. 8 times 9 times 1, 72. If you choose 0 in the tens digit, the argument's pretty much the same. You've got 9 choices for the units because you're not going to be using 0. You put a 0 here, that's only 1 choice. 8 choices for the hundredths digit because 0's been used, another 72. Now we come to this one. The units digit has not been chosen. The digit 0 has not been chosen for either the units or the tens. So maybe you picked a 6 and you follow that by a 3. Okay. Now, how many choices? So you had 10 choices here. Well, let's go the other way. You have there are 2 taken here then, a 6 and a 3. But 0 is also in a sense taken because it can't go here. So you've got 7 possibilities here. Okay. 7 choices here, 8 choices here, 9 choices here, for a total of 504. 7 times 8 times 9. So the grand total, when we add these 3 numbers together, is 648, which is exactly what we got before. This points out that even when the fundamental counting principle applies, you still have to decide the order in which you want to do the tasks. And sometimes it'll make the computations much easier than other times. Okay. There are 2 particularly special structures in combinatorics, simple structures. There are many structures, but they get quite involved sometimes. But on the simple side, there are 2 very simple constructions that are used quite a lot. And they are referred to as ordered arrangements of objects or sets and unordered arrangements of objects. And we're going to start by looking at the ordered arrangements. They are officially referred to as permutations in combinatorics. Here is a definition we're going to need. You may be familiar with. The product of the first n positive integers is denoted by n. That's an exclamation point, and this is read n factorial. And its value there is then 1 times 2 times 3 and so on up to n. So if n is 1, then you just have 1 on this side, so n factorial. 1 factorial would be 1. If n is 2, 2 factorial would be 1 times 2, and so on. Here is a little table for you to look at values. You can do this stuff on your calculator up to a certain point, but you do need to be able to do small values by hand. It's very helpful. You notice from the table that the factorials grow very quickly. By the time you get to 11 factorial, you're already at almost 40 million. Here is the official definition of a permutation. Start with an integer n and another integer k between 0 and n. A permutation of size k taken from a set of size n. So to do a permutation, there are two parameters: the size of the set, the parent set, you might say, or the universe, and then the size of the ordered arrangement that you wish to extract from that universe. So a permutation of size k taken from a set of size n is an ordered arrangement of k elements from the set. Ordered arrangements are also sometimes called sequences, but that's a term that tends to be used more in analysis than in combinatorics. And in calculus, most of the sequences are infinite. Here we're dealing only with finite sequences. The number of permutations of size k taken from a set of size n, which clearly does not depend on the set itself, but only on its size n, is denoted by p parentheses n comma k. This is common notation. And it was sort of necessary to make it clear that you're talking about a set of size n here. Could be any set of size n, and so it is clear that the number of permutations of a certain size k taken from a set of size n doesn't depend on whether the set is sets of numbers, or sets of matrices, sets of people. That's irrelevant. Only the size of the set is relevant. Here is a set x, 1, 2, 3, 4, 5, and these are the permutations of size 3. You grab three things and you place them in some order. 1, 2, 3, for example. 1, 3, 2 is the same set of elements, but in a different order. So this is a different ordered arrangement than this one. Okay. And so on. The complete list is much bigger than this, and we're going to, one of our next goals is to find a formula for p and k. So we'll know how many there are. This is not all of the permutations of size 3. Okay. The underlying set of a permutation is the set of elements that are used in the permutation. So, for example, these two permutations have underlying set 1, 2, 3, whereas these two permutations we just spoke of have underlying set 2, 3, 5. So basically you strip the order away and just keep the individual elements, place them in a set. Here is a set of 4 elements. Permutations of size 3 taken from x can be formed by taking all possible underlying sets. So those are the subsets of size 3, and they're listed here, and ordering each of the sets in all possible ways. So for the set underlying set ABC, we would have the permutations ABC, ACB, BAC, BCA, CAB, CBA. It's worth spending a little time absorbing the order in these permutations. What I did to create this list so I wouldn't miss anything is to say which are the permutations that start with an A, and those are A, B, C, A, C, B. Then once that's done, what are the permutations that start with B, BAC, BCA, and finally with C. If you are asked to write a list of permutations, it's a good idea to have a plan and not just to start throwing down permutations on the paper. It's also a good idea to know how many there are, which we're going to talk about in a minute, and so you can make sure you've got a complete list. But if you had to write down 24 permutations, and you count and you see there's only 23, it's going to be really hard to tell what's missing unless you have organized how you write them down. Okay. For example, you can immediately cut the list in half by checking the first, the number of permutations for each of the first characters. If there were actually cut it down even farther than that. When you, for example, in this case, I know that there's got to be 2 permutations that start with an A, 2 with a B, and 2 with a C. So if I had written these down and left off this one, let's say, now this is such a short list, you'd be able to tell what you forgot. But the idea here is there's only one permutation that starts with an A. And so you now know that what's missing is a permutation that starts with an A. So that sort of thing could be helpful. What about the actual value of P and K? Well, it's easily determined using the fundamental counting principle. So again, use your imagination. You have a set of size n, so it may as well be the integers 1 through n. And maybe think of these as golf balls numbered 1 through n in a basket. And you need to form an ordered arrangement of k of those. Okay. So you could do that with k tasks. First task, pick a golf ball. That's the number, that's the first number in your permutation. Second task, pick another golf ball. And you can't return the golf ball you picked to the basket. You gotta throw it out because permutations don't have duplicate elements. And so you keep picking golf balls, and you pick k golf balls. And you have built in the order by picking the balls one at a time. So you record the numbers on the golf balls, you get a permutation of size k taken from a set of size n. It's exactly what you want. So you have to perform k tasks, and the first task, this process does pass the requirements for the fundamental counting principle. The number of ways to choose any given ball doesn't depend on how the previous balls were chosen. No matter how the previous balls were chosen, the basket now has so many fewer balls. That's the end of the story. So the number of ways to pick the next ball is independent of what's happened in previous balls, previous choices. So there are n ways to perform the first task of choosing the first ball. Then there are going to be n minus 1 ways of choosing the second ball, n minus 2 all the way down to something, n minus something. But there are k factors here. Okay. So what this really is n minus. One way to tell this is how the product ends is to think, well, this is n minus 0, really, and then the next factor is n minus 1, n minus 2. So this last number, this number here, it counts the number of factors. This is one short of the number of factors, because n minus 0, n minus 1, n minus 2. 0, 1, 2. That's 3. 2 plus 1. Okay. So what you are doing here, if you want, so for example, if you want 3 factors, you would subtract 1, and that would tell you what the last digit is supposed to be here. So you want k factors, this is going to be k minus 1. And that's what it is, really. It's n minus the quantity k minus 1. But we write that as n minus k plus 1. Okay. This product is famous, and it has a name. It's called a lower factorial. And the common notation is you put the n in parentheses and you use a subscript k. This won't be recognized by everybody. It will be recognized by anybody who's taken a class in combinatorics or discrete mathematics, which is quite common. It should be in such a class. I'm not sure, but should be. But this term, lower factorial in this notation, might need some explanation. And this is the product. This is read n lower factorial k. And I'm going to leave it to you to show that the lower factorial can be expressed just in terms of factorials. N factorial divided by n minus k factorial. So you have to show that that fraction is equal to this product. And it's just a tiny bit of arithmetic. And take the advice here if you need it. Try a few small values for n and k. Okay. So, the number p and k of permutations of size k taken from a set of size n is then given by this formula. And lower factorial k, which can also be written as n factorial over n minus k factorial. When k equals n, in other words, when you are forming a permutation of the entire set, the number of ways of doing that is n lower factorial n, which is this product, which is n factorial. So the factorials are special cases of the lower factorial.